Make sure everyone's back, because if you sort of miss one slide, you can be lost very easily. Seeing seats fill up. We have 2 people missing. 3 people missing. 2 people missing. That's why it's nice with computers. You can count computers. No, there's still one more coming. Okay, so we'll get started because he already asked a question about the next slide. So I'll answer that, so we'll be okay. Okay, so let's move on to the second concept, which is samples and sampling distributions and sample statistics. So we can see, we said very briefly in the beginning that collecting information from all miners would be the best thing to do, but it's not the optimal thing to do in this situation. You might be outcompeted by another company who doesn't have to spend money on 48 samples. And these numbers are not very good, these numbers are not very representative, it just keeps things manageable. You can imagine a real mine's going to have a lot more employees, and when you scale up you can see that this is actually a real issue. So let's collect data from a sample now. So now we're consultants, so we're going to collect data from a sample, and we still want to be able to be informative. How do we do that with the sample and not with the whole population? So imagine that this is our population. What's a sample? A sample is just a group of entities from the population. So this could be a sample of 16 miners, and that sample now is going to have a set of scores, and we call those the sample scores. So x1 is score for person 1, x2 is score for person 2, and you can see they're both very stressed. x3 is the score for person 3, who's also stressed. x4 is person 4, just like before. So this is a really unhappy group. So that's the sample. That's, each number corresponds to a smiley face over here. Perhaps shouldn't use smiley faces in this situation. And so what we can do then is we can calculate a sample average. That's the first thing we want to do, right? We calculated the mean before, now we want to calculate an average again. How do we calculate an average? Exactly the same. We add up all the scores and divide by the number of scores. So it looks like this. All of the scores added together divided by 16. We saw before that this was the equation for the population mean. That's our statistical parameter. That's not what we're going to do. We're going to do something radically different. Instead of having a mu, we're going to use x bar. And that's it. So instead of having mu equal the mean, we're going to have x bar. That's our new mean. And that just indicates that this average is from a sample and not from the population. That's all it means.
What does x bar, what does that mean?
X, does anybody know?
Sample average.
Sample mean, sample average, an X with a line on it. That's all it means. So it just means sample mean.
But, and the other one was population.
Other one's population mean. So we do all the same math, we're just calculating these now. Yeah.
So in theory, if I understand this correctly, most of whatever research we will encounter using statistics, they will use a sample mean because you don't
have the population.
You don't have the population.
No.
Yes.
No.
So why do you teach us the mu and not the other one?
Because when statisticians talk about things, they talk about the platonic truth, which is the mean, and we want to start to relate our sample to the population. So we want to make inferences about the population. So we want to go from our sample mean to our statistical parameter, which is the population mean. Okay? So that's the process that we're going through. And that, for this sample that I picked out, is 26.25, a problematic group. So just remember that the population mean is the average score of the population. The sample mean is the average score of the sample. Or you can also think of it as an estimation of the average score based on the sample. So it's a guess of what the population average is. Okay? So it's a guess. It's an informed guess. And the information that we're getting is on the basis of a sample mean.
We have to qualify that with some figures.
That's what we're going to do. Yeah. So we've got a guess, and now we're going to go through the whole machinery to tell how good our guess is. Okay, so that's 26.25. So generally, we call this a parameter estimate, not a parameter. And all an estimate just means guess. So a parameter estimate is a guess about the population's parameter from knowledge about the sample. And that's a general thing. So anytime we've got a parameter, we can have, in a population, we can have a parameter that describes the distribution of a sample, and that parameter is a guess about the population. So we call it a parameter estimate. Works for means, works for standard deviations, works for everything else.
But that's almost never how you report data. You're almost never that careful or
No.
that reluctant to say you know anything.
No, and statisticians don't like that. No, you say the mean of the sample, but what you're really saying when you say the mean of the sample is your guess about what the population must be, and everybody knows that. That's the assumption. So that's easy, relatively, to calculate a sample mean. You just add up. It's the same formula. We haven't learned anything new here. We've learned a new concept, which is this concept of estimation, parameter estimation. Sample standard deviation is more complicated. So we saw before that this sigma is the population standard deviation. This is a parameter. This says something about the Platonic truth. And that has this formula, and we went through that on the board. S, which is helpful, because it actually is an English sort of, it's not a Greek letter, it's a Latin letter. Not Latin. It's from our alphabet, which I can't remember what it's called. So S is the sample standard deviation. It's a parameter estimate, just like before. It's based on our knowledge of the sample, which we're going to use to make an inference or a guess about the population. That has a different formula. What's the difference? Instead of dividing by n, we're dividing by n minus 1. And instead of having the mu, we've got, because we don't know the mu. It's the Platonic truth that we don't have access to. We have the guess about the mu, the guess about the mean. We have the x bar, we have the sample mean. Y minus 1. I'm going to semi-try to explain this, but I never do a good job of explaining this concept. This is the concept of degrees of freedom. So I'm going to refer you to the book and Wikipedia because I always mess it up. I know from experience that I've never explained this effectively. So I'm going to step back and go, here's a concept. And this is the only time I'll do this in the course of these lectures, because I do it poorly. But this is the sample mean. This is the number of scores divided by 1. Why n minus 1? Why do we have n minus 1? I'll give you my intuitive hand-waving explanation, and then I'll refer you to the rugby example, which is just a really nice way of explaining. So when we calculate a parameter in a population, we have all the information that we need. Because we know the population, we've got all the scores. We can reconstruct the distribution in Platonic truth space. When we use a parameter estimate, when we use sort of a guess, to estimate a population parameter, we need to use incomplete information because that's the nature of guesses. Guesses are on the basis of some information, but not all. And sometimes this guess relies on other guesses. And those guesses entail assumptions about other things that can't be changed. So in our case, our guess about the standard deviation has built inside of it a guess about the mean. So we're holding that guess stable, and we need to account for that. So we need to adjust our estimation based on how many assumptions we include in this way, or how many other guesses we include in this way. And we do this when we calculate for the standard deviation by using this n minus 1. And we put minus 1 because we're assuming one parameter. And that's the level, if you understand degrees of freedom on that level, that's fine. You don't need a deep understanding of this concept. So I've said this course is progressive. I've said that you need to understand every concept to understand the next one. This is an exception. Okay? And if you want a deeper understanding of it, then please look it up in the textbook. Yes?
But what do you mean by degrees of freedom then? So that's a concept. So this is how we do
Degrees
it.
of freedom is basically just counting the number of guesses that you've got, or that you've already made. So when you're making a new guess now, so before we were making a guess, and that was our first guess.
Yes.
And now we're going to make a new guess that relies on a guess that we've already made.
Yeah.
And every time we rely on a guess that we've already made, we do n minus 1.
I understand this bit, and this
Yeah.
is referred to as a more.
This is
more
before degrees
as
of
a
freedom.
degrees of freedom.
Yeah. Yeah.
Okay, because I mean, detracting one from n, that would do something to the value.
Yes. What would it do?
So it would make s bigger. Right?
Yes. Yeah.
Is that a good idea? I mean, is this a fair way? Is it just a choice?
It works for this,
Yeah.
and there's proof. So all of this is math.
Yeah.
So there's, and I'm not a mathematician, but there's logical proofs that say that this is all kosher
But,
and it fits a deductive system.
Not really, I mean, if we go back to
Yeah.
Hume or something, we can't really tell because we'd have to do the
But-
experiment over and over
But think
until
about-
eternity. Is that so?
Think about what it does though. It increases
It increases
our estimate of the standard deviation,
So it's okay.
which tells us about how certain we are about the mean.
Oh yeah, right.
That's what it does.
That's a good idea.
Yeah, it adds noise to our guess.
Okay, right, yes. Oh, that makes sense.
Yeah, so we're adding noise to our guess.
Yeah, okay, that makes sense.
What does that mean? You're adding noise to our
So we're less certain because now there could be more variability. We're assuming that there's more variability.
Yeah, right, okay.
We're adjusting for our guess by saying, well, there's probably more variability in here than we think.
Okay, that makes sense. Okay.
That works.
Can I write -2 if I have
If you have-
the parameters?
If you have two parameters hidden somewhere in here, then it would be n minus 2. And I find that that's the best way for me to explain
That's
it,
nice.
even though it's not strictly true, and even though it doesn't include all the mathematical proof for why it works. So I fudged this one. Also because I'm a Bayesian and I don't care about degrees of freedom. So we need to adjust our estimation based on how many parameters we got, and we do it this way. This concept's going to come up again, and again I'll fudge it there as well. But the Wikipedia page is a really good description, and the on degrees of freedom, and the textbook is a good description as well. Generally, mathematical concepts have fairly good Wikipedia pages because it's very geeky mathematical people that edit Wikipedia. Okay, so now we need to evaluate parameter estimates. So parameter estimates can be better or worse. So what does better or worse mean? Well, it means more or less true. More or less closer to platonically what's the state of affairs. So in our case, we've already calculated the truth. That's this population parameter. And this is why, again, we needed to talk about mu. Because now we can evaluate, we've got a benchmark. And we know that's 24.48 because we measured it. So our guess is 26.25. So it's not true. So it's wrong, but how wrong is it? And parameter estimates can be made better or worse on average by a number of different things. They can be made better or worse based on the representativeness of the sample. So yesterday we probably had bad parameter estimates for height because we had an uneven gender distribution between IKS and IKK. So we shouldn't make any inferences about whether one institute's taller or not because we've got a non-representative sample. The other thing is the size of the sample. So generally the bigger the sample, the better your parameter estimates will be. So what does that mean? Okay, so here's a population and here's a sample. We can talk about the population as a sample. We can sample everybody. And then that's perfect. We know we're going to get truth. We can make it smaller and miss a few people on the edges. And that increases the probability that the parameter estimate will be wrong. If we have an even smaller sample and drop out even more people, that increases the probability even further that we'll be wrong. If we continue to do that, we continue to increase the probability that it will be wrong. Won't necessarily be more wrong, but we're increasing the chance that it will be wrong. It's just like yesterday when we ran our simulations and we included 10 as a standard deviation for our deer study, and Anya got 7. That's because we were sampling. Random things happen when you sample. But overall, if we have a smaller sample, we're increasing the probability that we're going to get a parameter estimate that's further away from the true parameter. Yeah?
I'm just going to test if I have understood it correctly.
Mhm.
So every time you talk about parameters here,
Yeah.
it's always parameter estimates of the population that you want to refer to.
Yeah.
And then yesterday when we used variables,
Yeah.
so a parameter is a variable.
No. So a variable is stress.
Variable is stress, but you measure it, for instance, height and species.
Yes.
So
So height is a
height
variable.
would be,
Height would be a variable,
but
but
not a parameter.
height's not a parameter. The mean height and the standard deviation of height are parameters.
Oh,
So the variable's the thing you're measuring.
yeah.
The variable's the thing that can vary.
And parameter is exactly the statistical.
The statistical
result
description.
of
Yep. The statistical description
the-
of the distribution of the thing that you measure. So when we get to p-values and t-values and z-scores, they're not parameters either, because they're not talking about distributions. The word parameter is strictly reserved for distributions.
So parameter is the statistical distribution of what you want to measure with the variable,
Yes.
using the variable.
Yes, a parameter is something that describes the shape of a distribution, or the center of a distribution, or something else about a distribution, a feature of a distribution. And when we're saying parameter and not parameter estimate, it's the Platonic distribution that exists in the real world for statisticians. Okay. So the smaller the sample, and you get the intuition here, the less information. So the worse your parameter estimate's likely to be. Yeah?
I have a related question then. So you chose the number 10 yesterday for the deer study. So what could you relate that to what you just said? I'm sorry.
10 was our standard deviation.
Yeah. So that would
Yep.
be related to this example.
So
Can
for
you do that?
yeah, so if we're going back to our, we did the opposite of what we're doing now. So now
Yeah.
and that's simulation.
Yeah.
So now we're taking numbers and calculating from them statistical parameters.
Yeah.
So we're calculating standard deviation, we're calculating a mean.
Yeah.
What we did yesterday is we started with the parameters
Yeah.
and said, let's start from a normal distribution
Uh-huh.
and let's generate a list of numbers from that. So we've got a normal distribution that's got a center and a normal distribution and it's got a shape.
Mhm.
And let's pick a shape in advance, a priori, and pick a center in advance, a priori,
Uh-huh.
and then produce numbers that fit that distribution.
Okay. Very good. Thank you.
Yeah. So that's a really good question. Okay. So how good is my parameter estimate? What is it worth? So we know that our parameter estimate is going to be inaccurate whenever the sample's smaller than the population. So as soon as we drop one person, we're increasing the probability that we will have an inaccurate parameter estimate. It could be that by chance we drop somebody who's got the mean score, then it won't get worse, but there's a probability that it would. And every time we drop another person, we increase that probability. So big is better, but you can never really be sure. So if I can't be sure how good it is, can I estimate how good it is? Can I estimate how good my parameter estimate is? So now I want to make a guess about how good my guess is. See, statistics is all about existing in this Platonic universe of reality and then trying to guess what is out there in the non-reliable, unstable flux. So if I can't be sure, how can I guess how good my parameter estimate is? Well, we use something called the standard error, which is another statistic. What's the standard error do? Well, it's a way of estimating how well your parameter estimate that you've gotten from your sample represents the population parameter. Yeah?
How dependable are my data?
How reliable are my data? How will,
Okay,
if I run this again, will I get roughly the same
Okay, so
mean?
nothing like dependable variable.
No. No.
Yeah.
Reliable is a good way to think of it as well. Okay, so we're going to use this statistic called the standard error, and I'll go through and explain what the standard error is. So what's the standard error? Standard error is a standard deviation. But it's not a standard deviation, and a standard deviation, what's a standard deviation? It's something that describes the shape of a distribution. So we're going to describe the shape of a distribution, but we're not going to describe the shape of a frequency distribution anymore, of individual scores. Now we're going to describe the shape of a distribution of something called the sampling distribution. And this is going to be the frequency of scores from lots and lots and lots of different samples. Don't worry, I'll go through it. So what's a sampling distribution? Okay, so we've seen a frequency distribution. We've seen that that's just a plot that represents how often each type of score occurs, right? So we've got our population mean here. That's just a plot representing how often each type of score occurs. That's this curve, this normal curve that we saw. That's a frequency distribution. What about sampling distribution? What's that? Start by imagining, and don't worry about the logistics of how much this would cost. And we're trying to undercut other companies because we'll do some platonic tricks to get out of that problem. But let's just imagine that we have this strategy. We're going to bootstrap. It's called bootstrapping in statistics. Let's imagine we have this strategy where we're going to run multiple small samples. So we're going to take sample 1, and that gives us a mean of 27.16. So we're taking 6 people. Then we're going to take another 6 people, and that gives us a mean of 25.67. We're going to take sample 3, and that's going to give us some mean. And sample 4, and that's going to give us some mean. We're going to get sample 5, sample 6, all the way up to sample 40. So imagine we've taken 40 samples of this 48 people. Incredibly cost inefficient. But imagine that we did that. Okay? So if a frequency distribution is something that represents how often each type of score occurs, what a sampling distribution represents is exactly the same thing, exactly the same mechanisms, exactly the same rules, exactly the same formulas to calculate everything. But instead of representing how often each type of score occurs, it represents how often each type of sample mean occurs in our 40 small samples. So let's plot that. That's how our 40 small samples would look. My ugly plot. And that has a mean because that looks normally distributed, right? It has a mean. That should be close to the population mean, right? Because if we run lots of experiments over and over again, we should get really close to the population mean. So we're having lots and lots of guesses. And then we're going to take the average of all those guesses. And the average of all those guesses should give us a really good guess, and it does for this case. And that also has a standard deviation. So what does that tell us about? What that tells us is the shape of the sampling distribution. Right? So what does it tell us about what does the shape of the sampling distribution mean? What does that tell us about the world? Well, it tells us how much variability there is between samples. How much one sample, the average of one sample, varies from all of the others that we've taken. So it tells us the average distance of each sample mean from the average of all of the samples. So what that does then, it gives us an estimate of how closely any given sample mean we take is going to represent the population. So if this is really squished, then any sample is going to be good. If this is really fat, then every sample, there's going to be more risk inherent that we're going to miss the mean. We call that the standard error of the mean, which kind of makes sense. Standard, an error here sort of is more intuitive. How wrong is our guess likely to be if we did this? So there's 2 ways to calculate the standard error, and here comes a statistical fudge. One is obviously to do what we just did and take lots and lots of samples. Make a sampling distribution. Find the standard deviation of that distribution. And that would just be calculated in this way.
Standard error.
Oh, sorry. This is one way. Take lots and lots of samples, make a sampling distribution, find the standard deviation of that distribution. That's one way. Another way is to just do a fudge that just works but has been mathematically proven. So you sort of just have to accept it. I'm not going to go through any proofs. The standard error of the sample mean is equal to the standard deviation divided by the square root of the number of subjects. Don't ask me why it works.
No.
But that's the fudge. That's the fudge for taking a guess of the sample mean. But what we're hoping this tells us is really this.
Yeah.
Okay? And intuitively it sort of makes sense, because if you've got a really high standard deviation, but lots and lots of subjects, that number's going to be smaller. Got a really low standard deviation and only a couple of subjects, you should still be a little bit worried.
But if you
Yeah.
if you go back to the previous slides, this one.
Yeah.
So how do I know if this is wide? I mean, compared to the.
To compare to average, yeah,
Yes,
you,
I mean,
you
this looks
don't,
wide. But
this looks
isn't
wide.
wide.
This looks wide, but don't worry about it. All that you should worry about is this sort of conceptually. So the standard deviation divided by the number of subjects, which means that there's an inverse dependency between the number of subjects and the standard deviation. you've got.
So I'll get a number.
Yeah, and then
that's the number.
later we'll use this in inference.
Yeah.
So the absolute number doesn't matter, but we're going to use this in inference. So we're going to use it to calculate correct stuff. Okay, so we'll come back to it.
Yeah, yeah.
So as long as you understand that relationship and how it's built up and what it's supposed to represent, that's all that matters. So this tells us that if we've got a small standard error, there's not too much variability between sample means, so we've got a relatively good parameter estimate. So we're getting closer to Plato's truth.
So you can't report standard error without having different sample.
No, you can. You can calculate it like this. And that should give you the same as if you calculate it like this. This is a fudge, so that you don't have to go out and collect 40 samples to say something about the standard error. But it's a fudge that works, and it's got statistical proofs behind it. And it intuitively captures this relationship. The bigger the sample, the better our estimate's going to be.
But when you use bootstrapping innovation,
Yeah.
is that the same?
When you use bootstrapping, you're doing this. You're doing this thing of taking lots and lots of samples. Yeah.
So actually use the same one.
Yes. So there you've got a sample, and you're going to reanalyze your sample over and over again, which will give you a better average.
But here you don't have a test. So
Sorry?
you don't
No,
have
here you
a
don't. We're not doing machine learning. Yeah. So when you're doing bootstrapping, you're doing this.
So you just rely on.
Yeah. Here we're not doing bootstrapping. We're working within the Platonic world of null hypothesis testing. Okay. Machine learning involves reality. Okay. So that's sampling distributions and sample statistics. So now we can say more about this normal distribution that we've been talking about so much. This particular kind of distribution that has these particular parameters. Because there's different kinds of distributions with different shapes where there's different parameters that controls the way they change. We're talking about one that has two parameters, a mean and a standard deviation. So let's go a little bit more into details about this. Why? Because this is what we're going to use to do explanation. This is what we're going to use to do inference. This is what we're going to use to account for stuff. It's a normal distribution. Okay, so let's say we've got a decent sample and some decent parameter estimates. We've got a low standard error. We're comfortable. We're ready to go. Can we already start to make inferences about the population based on our sample of measurements? So can we go back to the mining company and say, your people are stressed? Not quite yet, because we need a statistical model. We need a statistical model to relate the sample to the population. Remember I said that first schematic at the beginning. And a statistical model, all a statistical model is a mathematical expression of the relationship between the parameters. So a mathematical expression of the relationship between the mean and the standard deviation. Okay, why do we need this? What does that do for us? So let's go through the logic. Let's go through the reasoning. Remember I said this yesterday. This is the scientific view of the world. We make observations, we construct explanations. From those explanations we generate predictions, and then when those predictions are right we use that to control the world. Where does our model factor in here? Where would a statistical model factor into this process? Well, it doesn't necessarily factor so much into your observations. It doesn't factor into the interventions that you run. It influences and basically frames the explanation of the predictions that you give. So what a statistical model is going to do is going to express your theory. And your theory can be very simple. Your theory can be the mind is stressed. It doesn't have to be any more complicated than that. So what we're going to do is construct a statistical model that expresses this theory that the mind is stressed. So what's a model? We need to sort of clarify the word model. And here I sort of steal Andy Field's way of framing this because I think it's a nice way to think about it. So we think about what happens in physics. There's all sorts of physical models. So there's these ideas that we can understand heat as molecules bouncing into each other. That's a model. That's a physical model of the world. We can't, well, back in those days we couldn't see the molecules. We couldn't see the bouncing. We just assumed that there was billiard ball-like things bouncing around with one another. We constructed an explanation based on that using mathematics and then made an inference to what must be happening, holding the physical parameters. Not statistical parameters, but physical stuff. Internally consistent. So that's what a model means. And essentially you can think of what, in constructing a model, what pieces of information do I need to highlight, do I need to keep, and what pieces of information are superfluous to the inference that I want to make. So the fact that the billiard ball is red is irrelevant to the billiard ball model of heat, of molecules bouncing around. And Field gives a really nice expression of this in his idea of a bridge. So you can think of models being relative always to some sort of task. So in building a bridge, you've got an engineering task. You've got a very specific task that you want to do in the world, and that is to end up with a bridge that looks like this. And you want to make sure that that bridge can maintain stability in the conditions in which it's in, which is the wind conditions, atmospheric conditions. So you've got your engineering task, which is to build this bridge. But the first step that you do is you're not going to go out and build the bridge and see if it falls over. You're going to construct the bridge according to mathematical principles and then probably test it, I don't know, in a wind tunnel. What sort of bridge, what sort of bridge should you make, should you construct? What's going to matter for the stability of that bridge? What's going to be superfluous and what's not? Well, this is a bad fit for the bridge, right? So this is, doesn't matter what colour the bridge is, but the fact that you don't have these pylons sort of coming up to hold the bridge stable means that you're not going to have any atmospheric, you're not accurately capturing the way that the bridge is going to interact with the environment. This is a better fit, and this is a good fit because it captures all the relevant stuff. It captures all the relevant and important stuff. So you can make a more complex model. You can get too complex because you can start to bring in superfluous things again. And the problem is that you don't really know when you're doing this, if you don't know the real truth of the world. But you know what you want the bridge to look like, so that's easy in this case, because you just make a bridge that looks as much like the one that you want to make and then put in a wind tunnel. And so what matters here is that you've got the right physical properties for the right conditions that you want to make your explanation in, for the task that you want to do, that you want to make your that you want to specifically physically do. You might be closer to that one over there. I don't know. No, we should. Sorry, I said I'd get an extension lead last time. Didn't know what I forgot. Okay, I might just push through anyway. So, if we've got a mechanical model, or we think of a description of a physical phenomenon and its most relevant physical properties, where what we're interested in is the physical properties, where physical here is relative to some sort of pragmatic goal, or explanatory goal if you're Lord Kelvin. Your statistical model has a similar sort of functionality, has a similar sort of job to do epistemologically. So it's a description of the phenomenon in terms of the most relevant statistical parameters that you want to explain. So it's in terms of the Platonic distribution of the way reality is, independently of all the noise and buzz of the stuff that we can measure. And what we're trying to do is to construct a statistical model that mirrors that reality in a way that serves our explanatory goal as best as possible. Okay? So Here we don't have an engineering task, we've got a research task, and that is to explain something. So our first step, instead of constructing a physical model, is to construct a statistical model. And our requirement, instead of being the right physical properties, is to have good parameter estimates, the right distributional assumptions, so that your assumption about what sort of distribution you think the measurements follow actually maps onto that platonic distribution that you've chosen, which in our case will be the normal distribution. And then that you've minimized all of this measurement stuff that you can get wrong as well. So we need models then here to postulate the relationships between parameter estimates and the relationships, most importantly, between the sample that we're measuring and the population that we want to say something about. Where that population is constructed as some platonic ideal that we can't get access to. In other words, to formulate and test hypotheses. Okay, so this is where we're going to have to start talking about probability. Because until now we've been talking about frequency. And that's worked so far, but statistical models aren't models of frequency, they're models of probability. So we're going to introduce some probability concepts here. So there's some new concepts coming. And we'll see how we'll go with that. So frequency we're comfortable with, that's just how often a score occurs in a population or in a sample. Probability is similar, but different. And it's importantly different. It's not how often it occurs, it's how likely it is to occur in a sample. Now, you heard me say before frequentist statistics, and you've probably heard other people say frequentist statistics. What frequentist statistics does is it treats probability as much like frequency as you can. Okay? So it says that how likely a score is to occur in a population is a reflection of how frequent it occurs in a population. And that's two sides of the same coin. So here, what we're going to do then, the main sort of mathematical concept I want you to introduce to understand probability is in terms of percentages. So rather than thinking of things occurring a number of times, think of things occurring as a percentage. Okay? So in our example, we've got this range of cortisol occurring 9 times. If we want to start to express that in terms of probability, we want to express it in terms of the percentage that it will occur. So it will occur 18.75% of the time. And that's just 9 divided by 48. Times 100. But probability doesn't express things from 0 to 100 like percentages does. It expresses them from 0 to 1. So we just divide it by 100. So probability is always from 0 to 1. So the probability of getting this score is 0.187. But if you're comfortable to just translate that into percentage in your head, feel free to do so. Okay?
We don't need to know why probability is always calculated from
0 to 1. It's arbitrary.
Yeah.
And it makes the math easier to work with, makes the equations more elegant. And here, 0 and 1 represent something specific. What does 0 represent in this case?
That it won't occur.
That it can't possibly occur. It's impossible.
Okay.
What does 1 represent?
It did occur.
It did occur with certainty.
Yeah.
And everything else is in between.
Yeah.
And 0 and 1 sort of fit that way of thinking. Okay, so we've got frequency distributions that we've talked about. Now we're going to talk about probability distributions. And this thing of sort of framing everything in terms of being from 0 to 1 ends up being really useful. This one little change that we do allows us to do something new that we couldn't do with frequency distributions. So let's look at probability distributions. And we're going to be playing a little bit around with probability distributions just for fun this afternoon. Okay, so a frequency distribution is a plot. We saw that. It represents how often each score occurs. A probability distribution is a plot too, and it represents how likely each score is to occur. But now, we don't have real measurements that we have to put into bins in order to get some sort of structure. we can say for each infinitesimally small item, what's its probability if it follows the same sort of shape. We're not constrained by measurements anymore. Now we're in the Platonic world, so we can do more math. We also call this a probability density function. We'll be using density functions this afternoon. But all that means is, what is the probability of something happening? We can think of density is how dense is the probability for each score. Okay, so probability distributions have some are a way of representing numerical ideas that we just talked about. This idea from 0 to 1. 1 means it's definitely going to happen. 0 means it's definitely not going to happen. If it's from 0 to 1, then there's a chance of happening. So, for example, the probability of rolling a 4 on a dice is 1 in 6, because there's only one 4 on a standard dice, so it's 0.16. So it's 16% chance that you'll get a 4. So how does a probability distribution then represent this chance of stuff happening, chance of a value occurring? Because that's what we want our distributions to represent. Okay, so here's our probability distribution. And let's say that this is sort of a curve. This is a shape, right? And it's a shape that is asymptotic, which means that all that means is it doesn't touch here ever. You can go off to infinity and it never touches, but we can treat it as though it does. There's a finite area under this curve. There's a finite shape here. It's like if I drew a circle on the board, there'd be an area in that circle that we could calculate. Okay? And let's arbitrarily say that the area under that curve is equal to 1. So the area of that circle, if it's helpful to think of it as a circle, is equal to 1. So we've defined that definitionally a priori. It's equal to 1. That area is 1. This is actually a really sensible thing to do, and it should spark your intuitions. Why does it make sense that we mandate that that area under that curve is equal to 1? Yeah?
You'll be the same as 100%.
Yeah, same as 100%, yeah. Well, you're going to get some score. So if we think about the meaning of probability, 0 equals not going to happen, for sure. 1 equals going to happen, for sure. If you're measuring cortisol, you're going to get some number. And so it's certain that you're going to get a number. So if you look at every possible score, you actually want it to equal 1. And then now, we can represent the probability of getting a single score. And the way we do that is to just look at the point on the curve. So the probability of, say, getting this value, so if this is the score and this is the probability of getting this value is just here. Okay? What do we do if we want to look at the probability of getting a range of scores? So if we want to look at the probability of getting, say, between 16 and 20 micrograms per deciliter of cortisol. Yeah?
We measure the area.
We measure the area. We measure sort of that segment under 16, 20, point on the curve, point on the curve. That's the proportion of certainty something's going to happen. This thing's going to happen. This specific score is going to happen. Is the area under that curve for those scores. Is that okay? So now we can use calculus. We're not going to, but we could. Okay, so probability distributions. Other than that, they're just frequency distributions. Yeah?
What is the center?
What is the center? Well, that's what we'll get to now.
Okay.
I mean, probability distributions, they're just distributions, right? So they have a mean. Here, this has a mean and a standard deviation. We saw this with the frequency distribution. Probability distribution is the same shape, so we can treat it as having all the same properties. It has a mean, which is the center, and a standard deviation, which is the shape. Because this is just a reformulation of this in percentages. That's all we've done, is we've changed this to percentages rather than frequencies. So this x-axis here, this y-axis, sorry, doesn't mean frequencies anymore. Now it means percentage of happening. So all the properties of this will be retained when we go over to this. So it has a mean and it has a standard deviation. It has parameters. So when I was saying before that there's a distribution off somewhere in Platonic reality, which is true, this is the one I was talking about, is the probability distribution. Okay? And so there's a particular kind of probability distribution that gets used a lot in this kind of statistics that we're talking about, and that's the standard normal distribution. What's the standard normal distribution? A standard normal distribution is a distribution where the mean is equal to the center of the distribution, and one standard deviation is equal to 34% of the values, just by fiat. So we've said that one standard deviation is equal to 34%. What does that mean? Well, a standard deviation of 1 is equal to 34% of the area of the total curve. And this actually gives us a model. So how can we use this to relate this mean and standard deviation mathematically? How is it really a model? Well, we can write an equation now that we've got all of these properties that includes only the mean and the standard deviation and gives us all of the facts about the distribution that we can completely regenerate the distribution on the basis of. It's called the Gaussian function. It looks like that and you don't have to think about it. But it exists. So that function has got a mean and a standard deviation, and from that we can regenerate the whole distribution. And that's what your computer did yesterday when you were running R0. Okay. So a couple more slides and then we'll have a break. Which will be awkwardly timed because the sandwiches aren't here, but anyway. So this standard normal distribution is seen to be a very important statistical model, a very useful statistical model. Why? Because it's presumed to be very, very common. Actually, do you know what? I'm going to have a break. I don't want to overload you. So let's stop for 15 minutes. Let's stop for 15 minutes and then we'll come back and have lunch at 12. Good. Yes. Let's have lunch.
So when I run a binomial.
Yeah, binomial. That's a different model. Yeah, a binomial is a different model. So a binomial is if you're tossing a